In today's video, I'm going to talk about Kekule, his ideas of the structure of benzene, and I'm also going to talk about the delocalized model of benzene, and I'll also be doing a few questions and answers at the end from the book. Kekule knew and had previously worked out that benzene had the chemical formula C6H6. However, his structure failed to explain the chemical properties and reactions of benzene. That's why many scientists disagreed with him. Kekule claimed that benzene had a cyclohexagonal shape containing 3 double carbon-to-carbon bonds and 3 single carbon-to-carbon bonds, like I've just drawn. However, there were some faults with this idea. First being, if there truly were carbon-to-carbon double bonds, benzene should react like other alkenes. For example, alkenes containing carbon-to-carbon double bonds, when reacted with bromine water, would decolorize the bromine water. However, this was not the case. Kekule went on to argue that benzene was constantly in an extremely fast equilibrium, changing the position of the double bonds. Kekule claimed the reason for the lack of reactivity was that an approaching molecule, such as a Br2 bromine molecule, it couldn't attract to the change in double bonds. In 1922, a lady named Kathleen Lonsdale used X-ray diffraction, and this helped her find out the correct structure of benzene. Using X-rays and this process, also known as X-ray crystallography, she was able to find that all the internal bond angles were the same 120 degrees, and she also found out that all the C to C bonds were the exact same length. So, systematically, Kekule's idea of benzene is actually cyclohexa 1,3,5 triene. When an alkene reacts with hydrogen, the energy change is called the enthalpy change of hydrogenation. With cyclohexene, with one carbon-to-carbon double bond, when this reacts with hydrogen, the enthalpy change of hydrogenation is minus 120 kilojoules per mole. Kekule's benzene, with 3 carbon-to-carbon double bonds, would be expected to have an enthalpy change of hydrogenation of minus 360 kilojoules per mole, 3 times that of cyclohexene. However, when benzene is actually hydrogenated, the experimental value of the enthalpy change is minus 208 kilojoules per mole. So this is 152 kilojoules per mole less than the expected enthalpy change. So this shows that benzene is more stable than a compound that contains carbon-to-carbon double bonds. This once again disproves Kekule's structure. So now I'm going to go over 3 quick questions. Question 1. What would you expect to see if cyclohexene reacted with bromine? Write an equation for this reaction. As you know, the bromine molecule would react with the carbon-to-carbon double bond, and the bromine would decolorize. And here is the equation. Question 2. What type of reaction takes place between alkenes and bromine? A reactant is added to an unsaturated molecule to make a saturated molecule, so this is an addition reaction. What technique was used to show that all the bond lengths in benzene are the same? This is X-ray diffraction or X-ray crystallography. So now I'm going to talk about the delocalized model of benzene. The delocalized model consists of the following features. Benzene is a cyclic hydrocarbon that has 6 carbon atoms and 6 hydrogen atoms. Each carbon atom is bonded to 2 other carbon atoms and 1 hydrogen atom in a planar hexagonal ring. The shape around each carbon atom is trigonal planar, and the bond angle around each C-C-C bond is 120 degrees. Each carbon atom has 4 outer shell electrons. 3 of these electrons make bonds. These make sigma bonds. 2 of them go to the other carbon atoms, as I've said earlier, and 1 goes to hydrogen. Now what this does, this leaves an electron in a 2p orbital to orbit above and below the plane of carbon atoms. I'm quickly going to refresh your memory from the last year about how the p orbitals overlap. Here we've got the p orbitals. Here you've got the electrons in the p orbitals and then the original sigma bond between the 2 carbon atoms. Then p orbitals sideways overlap to form a pi bond. The sigma bond remains still, but now you've got a sigma bond and a pi bond. So the same thing happens in benzene. Here we've got our p orbitals on each carbon atom above and below the plane. The p orbitals on each carbon atom all overlap each other, and this leaves us with a ring of electron density above and below the plane. So the overlap produces a pi system, which is essentially a system of pi bonds above and below the plane, as I've already said. But all the p electrons are now covering the whole ring, not just one carbon atom. The delocalized system has 6 electrons in total. If you remember earlier, I spoke about how benzene was more stable than expected. This increased stability means that benzene struggles to take part in addition reactions. Under normal conditions, benzene does not decolorize bromine water, react with strong acids such as HCl, react with halogens such as Cl2, Br2 or I2. If an addition reaction were to occur, the product would be less stable than benzene and the reaction would not have been energetically favourable. So instead, substitution reactions occur. One of the hydrogen atoms of benzene is replaced by another atom or group of atoms. The organic product that forms retains the delocalization, and this allows the stability of the benzene ring to be kept. So now I'm going to quickly go over the questions. Question 1. State the shape and bond angles around a carbon atom in a benzene ring. As I mentioned earlier, the shape is trigonal planar, the bond angle 120 degrees. Question 2. How is the delocalized ring of electrons formed in benzene? This question here basically covers everything we've done today in a short section. P orbitals overlap sideways to produce a delocalized pi cloud containing 6 electrons above and below the plane. Finally, what does delocalized mean? A delocalized electron is an electron that does not belong to one specific atom. It may have originally, but now it's shared between 2 or more atoms.